Okay, I think we can start. It's 11:15. So hi, my name. So this talk is called Beautiful I/O, and in the next couple of minutes, I would like to take you to on a tour through the standard library package I/O and various implementations of its interfaces. Maybe just a few words about me. Just a second. Just a second. Excuse me. Yeah, just a few words about me. I work as a software developer in Leipzig, Germany. I work at Leipzig University Library. We are involved in a couple of open source projects in various projects in the library domain: catalogs, repositories, digitization, data acquisition, processing, and indexing. And we use Go for a couple of tools and also internal services. I'm also one of the organizers of our local user group, which is like slowly growing. And in 2017, I did a workshop at GoLab 2017, which was called Explore I/O, and which is where this talk also came from. So for this workshop back then, just a bit of background, I watched a presentation which a couple of you or many of you have seen, which is called Go Proverbs. So Go Proverbs are these informal kind of hints and rules about software design related to the Go programming language. There are a couple of proverbs, and one of them mentioned in this talk was, the bigger the interface, the weaker the abstraction. And two of the examples that were mentioned in this talk were io.Reader and IOuWriter. And this talk is by Rob Pike, and he goes on and says that it's a very special thing in Go that
all the people who have no seat can go in the other room, in this one room.
Okay. Also, all the people who don't have seats can go into the other room, I'm told.
On the side.
There. Okay. So the interesting thing about these interfaces in Go is that they are really small. They have just a single method. And in the talk, it's mentioned that Rob Pike says he implemented like 20 different implementations of io.Reader in a single project. And back then, I haven't implemented a reader myself. Really, I knew about these interfaces, but haven't really used them. So I was curious, like where are these interfaces actually used, and what you can actually do with them. So this was the question. I prepared some material, did this workshop, and now I'm trying to compress this into 20-25 minutes, what I've learned, and kind of show you what a reader is, how you implement one, and where it's actually used, and show you a myriad of examples. Okay, so the I/O package contains basic, widely used interfaces within and outside of the standard library, and a couple of utility functions. Why beautiful? Well, it of course depends on the the beauty is in the eye of the beholder, but the interfaces are small. You only have to implement a single method. We see a couple of implementations that fit on a slide completely and still do something useful. They are adaptable in various places and composable. I think these are all a lot of like good properties to have for software. io.Reader, interestingly, also gets a lot of praise and love from people. So I found a couple of mentions of io.Reader where people say or write articles to convince you to use io.Reader in your code whenever you can, or love letters are written to the Go io.Reader. Or it's a favorite interface of others. Okay, so what's in this package? What is in this package I/O? There are 25 types. 21 of them are interfaces. There are a couple of functions, a few constants and errors. Here are some concrete types, which we don't go into, and there are a couple of functions, copy, and we look at a few of them, but not all of them. The core interfaces are io.Reader and IOuWriter. They read and write. There are a couple of other single method interfaces like closer and seeker with a close and seek method. And then you get these combinations of these interfaces like ReadWriter, ReadCloser, ReadSeeker, and so forth. you see that not all combinations are there. So if you need something else, you would have to write this yourself. For example, here's a project, Go4, which is from a utility library from the PerKey project, and somebody needed a read closer. Well, you can simply construct this yourself. So how many readers and writers are there? So I asked the Guru tool for the implementations of the interfaces, and I counted over 200 implementations of each IOReader and IOWriter in the Go tree, and a few of the sub-repositories, not all of them. Okay, so what is a reader? It's simple. It's a single method called read. It takes a byte slice and returns the number of bytes read and possibly an error. The reader implementation will populate a given byte slice. So you give it a byte slice and the reader populates it. You can read only at most length p of bytes, and there's a special error value, which is not really an error, more of a sentinel value to signal the end of a stream, which is called IOEOF. There's some flexibility around the end of the stream. So when a stream ends, in the case of the reader, if n is larger than 0, then before considering the error, you might want to actually handle the bytes, which is maybe a bit different from other error handling in Go, where you don't necessarily have to look at the return value. I mean, it's not a return value. You pass the byte slice in. Doing so correctly handles IO errors that happen after reading some bytes, and also allows both of the allowed EOF behaviors. And both EOF behaviors are, you either can exhaust the read and then return N0 and IOEOF, or you can return IOEOF with the last number of bytes that you read. Okay, a few more notes on this reader. So the byte slice that you pass in is under the control of the caller. You are not returning a byte slice that you read. If you would return a byte slice, the read implementation would have to allocate this byte slice over and over again when you read a stream, and this would cause quite some pressure on the garbage collector. Implementations must not retain P, so it's the property of the caller is the owner, and this also hints at the streaming nature of this interface. So we talk about possibly infinite amounts of data, but we at the same time talk about a fixed size slice that we need to fit this in. So there's no hint about the size. It's just we stream over this data. A couple more notes. The read function does not guarantee that the passed byte slice will be completely filled. So it might just read a single byte or a few bytes. And sometimes you have a problem where you actually need to read at least a number of bytes or the exact number of bytes. And there are two functions in the IO package that allow you to specify exactly that. One is called read at least, where you read at least a certain number of bytes, otherwise fail, or read full, where you ask the read, where you ask a reader to fill up a byte slice completely or fail. So the implementations of these can be a wide variety of things. So readers can be files, network connections, HTTP response bodies, standard input, compression, serialization, and writers are used also for similar purposes, and hash functions, standard output, formatting, and more. Here's a question I found on Stack Overflow from 5 years ago. Create an IO reader from a local file. So someone has a file and has an API where a reader is required, and ask like how I actually convert this. So Go has this structural typing. If a type implements a method, it is used everywhere where an interface which has the same method set or matches the method set can be used. And so you don't have to convert anything. You can just use an an OS file where an IO reader is required. There's another function or another like utility package which is called IOutil. It's a companion package. It's much smaller, has a couple of utility functions for temporary files, and one of the functions there is IOutil ReadAll. And I see it quite often in code, and the reference love letter in the beginning points out that IOReadAll is not something that you necessarily need. So it's in the standard library, it's useful, you sometimes need it, but it's sometimes also overused. So let's look a bit into that. So what IOUtil ReadAll does, it takes a reader and turns it into a byte slice. So basically you're going from the streaming realm to a byte slice which contains all the data. If you do that, you may lose the advantage to use this reader in other places. You also consume potentially much more memory, because you have to hold it all in memory at once. And these streams can trivially produce infinite amount while using barely any memory. Imagine an implementation behaving like def0 or defuRandom. So memory control is an important advantage. And you lose some of that if you use this IOUtil ReadAll. So sometimes I see this in code. Instead of so you have some response body maybe from an HTTP request response, and the IOUtil ReadAll is used to get all the data out. And then, for example, you are writing a curl implementation in Go, and you just want to print out the body. Then you say format print line and then string B. I see this code, and I think there is a better way, because we are coming from the stream realm. Response body is a ReadCloser. And here we just want to print this out, and standard out is also a stream. And for that, there is this IOCopy function, which basically connects readers and writers. So you have a source, which is the response body, a destination, which is a reader, a response body, which is a writer. An IOCopy has an internal buffer and reads successively from a reader and writes to this writer. So if you follow this stream, so in the above example, you could have like gigabytes of response body, which you have to hold all in memory, whereas in the lower example, you have this internal buffer, and this is all that you use, and you still have this same result. Basically, you're writing the result to standard out. So try to follow the stream if you can. Because they are memory efficient, they can work with data that does not fit in memory. It allows you to work on different protocol parts differently. For example, HTTP headers are usually smaller than a possibly large HTTP response body, so readers can be useful there. One other example that I sometimes see, although it's kind of maybe not as pronounced as the former example, is when you work with data, like for example JSON data. We need to unmarshal this. The unmarshaller takes a byte slice, and you like deserialize it into a value. And this data might come maybe from IOUtil ReadAll, because you are kind of reading all the data, then you want to unmarshal this. But there is actually another way that is supported by the JSON package, which is a decoder, and a lot of other packages have this as well in the encoding, where you create a new decoder which takes a reader. And so you don't have to have this intermediate step of this byte slice. You can just pass in the reader and then decode on that reader. In this case, the example is a bit weak, because the JSON data has to be read in whole anyway. But there are examples where this wouldn't be the case, and this would be more memory efficient. These things compose, of course, well. Here's a gzip reader that on the fly unzips some reader response body, OS standard in or something, and then passes this reader into a decoder and then decodes it. I forgot this value. It should be %v. And so if you stay in this realm, you can get really kind of a lot of things done in a few lines. So how do you implement a reader yourself? It's just a single method, so it's it can be like not a lot of work. So let's look at a very simple example. Let's implement def0. We declare a type, and then we declare a read method, and then this read method gets this byte slice, and we are asked to populate this. And here I'm just filling it with the 0 byte and returning the length of p, like the size of the byte slice that we got, and nil. So this never fails. So this is already an infinite stream, and it's just a few lines, and can be used in all places where a reader is required. Of course, you are not always just free to add your data yourself. You are wrapping another reader. So as an example, here is an upper reader, which has an underlying stream or a wrapped reader. This upper reader takes whatever it gets and uppercases the bytes and then returns that. So you would define a type, have this underlying stream, implement a read method, which reads from the underlying stream, but before returning, just executes bytes to upper and like replaces this byte slice with bytes to upper and then return this. And with just a few lines, we have this filter. And here's a usage example, again using IOCopy. We have OS standard in. We wrap this in an upper reader and copy it to standard out. So we have a filter where we can pipe something in on the command line and it uppercases all the bytes. And this works with infinite streams. We don't have to care about like how big this is, where this data comes from, like from a response or from a file. And yeah, it's memory efficient. If you want to exercise this yourself, may I just ask, have you implemented or have you done the Go tour and actually implemented this exercise, this ROT13 reader? Can you just show of hands who did this? Okay, a few hands. So I really recommend this as a fun exercise. It takes a few minutes to kind of wrap your head around, but I hope I gave you some kind of hints on how to do that. Okay, let's briefly look at IOUWriter. It's quite analogous. Writer is a write method, has a single write method, takes a byte slice. This byte slice is then written to whatever the implementation provides, returns the number of bytes written and then possible error. It writes to the underlying data stream, and it will return between 0 and length p for the value of n and any error if it occurs. If n is less than the number of bytes, the length of the byte slice, you must return a non-nil error, and the write implementation must not modify the slice even temporarily, and implementations must not retain p. So again, we have this byte slice under the control of the call side. So here's another example which I use quite often on the command line, def null. It's a sync where all the bytes are discarded. We define a type, we define a write method on the type. In this case, I wouldn't have to use the pointer interface. And then we just return the length of the byte slice and nil. So we just say, well, we processed all the bytes and there were no errors. So it's a sync. And we can just use this def null where we can everywhere we are requiring a writer. So I'm having a string here wrapped in turned into a reader and then like copied into def null. So this would do nothing except IOCopy would report the number of bytes copied. The standard library implementation of this def null is called IOUtil discard. And there's an interesting / frustrating bug related to IOUtil discard. If you're interested in like very subtle race conditions, it's in issue number 4589. Okay, let's go a bit more into the use cases where these things are used. So you can abstract a physical resource. You can convert something that is not a stream into the streaming realm. You can define buffers. You can enhance functionality. You can decorate, transform. It's used a lot for testing, mocking behavior, and also there are a lot of like utilities that you can write around these interfaces. So let's briefly look at a couple of things where you can use these things. So OS file is like a prototypical stream. You read a file. There are some alternative implementations like atomic files in third-party libraries, which are really useful. Just a historical note on this file idea. There's a very nice documentation from 1982 about Unix. And there are some interviews, and in one, a file is described. And I just read 1 or 2 sentences. A file is simply a sequence of bytes. Its main attribute is its size. By contrast, on more conventional systems, a file has a dozen or so attributes. To specify and create a file, it takes endless amount of chit-chat, and so forth. And Unix, of course, has this idea of a file is just a sequence of bytes. It wasn't like this was a real simplification at that time, because it seems like other systems were not really that that simple. And my take on this is that if a file is just a sequence of bytes, then more things start to look like files. So let's look at a couple of them. Network connections. There's this netcon interface. It requires like read and write method on the implementations. So if you are, for example, creating a connection with net.dial, you can then have something where you can just write to, like standard out or a file you can write to a connection. And here I'm using a utility function called io.WriteString and just make a HTTP request manually. You can convert things that are not really streams into streams. Strings.NewReader does that for strings, bytes. NewReader does that for byte slices. There's a type which you probably use because it's quite versatile, which is called bytes buffer, which is a variable size buffer of bytes with read and write methods. So it's a byte slice, but it can be used at places where reader and writer are required. The zero value is already useful, and so we can just declare a bytes buffer and write to it, and then have some utility functions to get the string back or the bytes back. There are some enhancements. For example, buff.io.Reader takes a reader, it wraps an IOReader via writer, similar to as we have seen in the smaller examples. So this is the implementation from the standard library. You have this underlying reader provided by the client, RD, then you have this internal buffer and then some bookkeeping. And it wraps an IOReader writer, creating another object that also implements these interfaces and provides buffering and some helpful textual I/O. So you can have a couple more simplifications, for example, reading up to a certain delimiter. You can very simply implement line-wise read over line-wise files. And then there is another abstraction built on top of that, buff.io scanner, which takes a byte stream, which takes a stream and chops it up into tokens by defining a certain split function. On the writer side, there's a package TabWriter, which is also a filter. It implements the write interface. You just write your data that contains tabs or new lines in there, and it will write out a nicely formatted table. So you can use this as a filter. Compression algorithms use this interface too. So here I have some data. I wrap it into a stream, bytes NewReader data, and then I decompress this and print it to standard out. So I don't have to go through intermediate steps. Once I'm in this streaming realm, I'm getting up to standard out and can print this out. I personally am a big fan of a tool called PigZ, which is a parallel implementation of gzip. And there's actually a Go kind of equivalent parallel implementations of the standard library compression algorithms in this repo, which is quite nice. Okay, we already saw serialization. We have this new decoder in a couple of encoding sub-packages, for example, base64. You see that it creates a base64 decoder, and it keeps the same interface. Like you give it a reader, and it returns a reader, and all you have to do is like specify the kind of encoding that you want. And we saw this with JSON as well. You can have this new encoder where you just specify a writer, and then encode value after value onto the stream. Okay, let's look at some strange example briefly. So here is so imagine you're an archive and you have to kind of black out certain certain parts of your data. So for example, I have here some text and I want to kind of define some words that I want to black out, and I want to do this in a streaming manner. I can, it's a bit small. I can have a type that implements that, have an underlying reader, and then have some replacer that on the fly replaces and blacks out certain things. So we have this read method. We read from the underlying reader and then do this transformation. So so here I'm defining a couple of words that I want to like erase from my text, and then like take this string, turn it into a reader, and then do this copy to standard out. So let's see how this works. If I just run that, I get back like the same stream, but like some parts of it are blacked out. So this is also like a stranger implementation of some transformation. One interesting thing is that you can mock a lot of things with these readers and writers for test purposes, simulate failure cases, or have infinite streams. This is one thing from some test function in, I think, standard library, where you have an infinite reader. Basically, you have a buffer, and you infinitely loop over this buffer. This never ends, and you can test your implementations on how you react onto streams that never end. I have an example of a slow reader here, which slows down reads. It's quite short. We have like a channel that actually is a ticker, which allows only at certain time intervals a read to happen. And then furthermore, we are not reading the whole byte slice that we are giving, but we are creating like a smaller, like 1 byte buffer or byte slice and read into that. So we are very, very slowly progressing on this stream. And I can use the same interface, copy to standard out, by creating this new reader. So let's look at how this would look like. And then I would get like one kind of input and just slow it down. So you can see like maybe you want to test like how fast your website renders, or some other parts of your program react to like slower connections or something like that. There are more test cases in the standard library. Buff.io test has something similar, like slow reader, error then good reader. So you can like simulate some failures which then recover from themselves. Fault inject reader. Here's an example from Kubernetes, which is a read delayer, which just delays a read. And I think one example is using 30 seconds. So what happens to your component when the other component takes like 31 seconds to respond? Because 30 seconds is a typical timeout for network connections, and how you handle these cases. Yeah, and then you have a lot of like smaller utilities which maybe don't even touch the stream at all. You just do them for the side effects, or you have some patterns that you want to repeat, some things, sources. Maybe you want to impose some limits which don't touch the stream but only limit like the time that you have to read it. You can use it for error handling. You can split streams, merge streams. So let's look just briefly at a couple of them. So the equivalent of the length function in the streaming realm would be a count reader, where you are reading and you're not touching the stream at all. Just in between, you are adding to an internal count variable, and you use an atomic count, so you might be able to safely count the number of bytes read, and then you expose a function that returns this number whenever you are interested in that. You could, of course, like use IOUtil ReadAll and then take the length of the byte slice, but again, this might be not the most memory efficient solution. Other stats are possible. Here's a small example of a language guesser that works in a streaming fashion. So I have a couple of example texts in Italian, English, and German. There's this trigram maps that float around the internet, where you have typical trigrams for each language. And this trigram guesser has an internal IO reader. The read implementation doesn't do that much. It just returns the stream unchanged, but as a side effect, we are counting these trigrams up. And so we can, this trigram type has a guess method that allows us to ask, like, what was the stream probably about? Like, was it German, English, Italian, and so forth? And we can use IOUtil discard, so we are copying we create a new guesser from the stream, and then just pipe it into IOUtil discard, because we are not interested in the stream. We just want to have the side effect of what the guess would be, and in this constructed case, it actually works perfectly. So the guess is exactly the same that you have there. Yeah, so you can potentially have like windowed analysis of streams and be memory efficient in that way. There's an example in the CSV package in the standard library in reader test, which is n times reader. It just yields the string s n times, and it used to generate it is used to generate test data to benchmark the CSV implementation. So instead of writing fixtures and files that have a certain size, you are just generating these file-like things or these streams that then the implementation can use to kind of or this test can use to benchmark the parsing. You can generate infinite data. We already saw the zeros. We also have like a random data source. So if we would want to have a password generator, we could connect our base 64 encoder to standard out, and then use from the crypto-rand package the reader, which is a globally shared instance of a cryptographically secure random number generator, and then copy this into our encoder. And there's a utility function called copyN because it is an infinite reader, but we just want, for example, 16 bytes, and then have a like printable representation of that. So we could run this and get back some random like password suggestion here. So this would be a use case for this copyN function in the IO package. You could implement a timeout, which again doesn't touch the stream at all. It just kind of imposes a limit. We can quickly look at this as well. So we have a timeout reader. It takes a duration and then uses this timeout pattern where we start the read in a separate Go routine and then select whether we first encounter the timeout or encounter some result from this read. And we simulate it by, or we're testing it by implementing another reader, which is just slow. It sleeps for a number of seconds before it reads, so we can test this implementation. We have a timeout reader that reads from a string with a timeout of 100 milliseconds, which should always succeed. And then we have a slow reader, which takes like half a second to respond, and it should time out. And if we test that, sure enough, we are getting hello world from the string, and we get this timeout arrow from passed through IO copy from this timeout reader. And there, yeah, so we are kind of coming to the end. A few more utilities that are in the package. There is a T reader, which is modeled after this T command, which takes a stream and allows you to get a new reader out, but at the same time, when you read something from a reader, it also writes to another writer. So you have you can have a T reader process, for example, your response body at the same time, write it out to a file. There's a utility in the IO package which is called multi-reader, which allows you to take a variable number of readers and expose them as a single one, which can also be useful, maybe to unify many things of the same kind or multiple or different kinds. There's an example of ReadCloser, just as an example that sometimes you have to go back into this non-streaming realm if you want to do some of this stuff. This is from the IOutil package. It takes a ReadCloser, which is the response body, and it returns two ReadClosers that are actually contain the same content. But the implementation is like this, that you first have to actually read the whole thing into a byte buffer, and then you have like you have to keep it in memory, and then to have the same interface, you are returning the buffer. You wrap it into a knob closer, which is which takes a reader and adds a close method, which does nothing to it. So it satisfies, for example, the ReadCloser interface. And we cannot just replicate that because we would exhaust the this ReadCloser in the first instance. So we have to actually get the byte slice out, which makes a copy, turns it into a stream, wraps it into a knob closer, and then returns that. So this is an example of from the yeah, HTTP util dump package. Yeah, and here we use a multi-reader to read both of them, and they would just yeah, duplicate this hello gophers. Yeah, and you can do all kinds of. I mean, by now you see like how versatile these things are. So you can do all kinds of crazy things. For example, if you want to have like some events at certain points in a stream, like maybe you want to do something at IOF, you can just wrap this in an io.Reader, have some kind of callback function, which is just a dummy function. It doesn't even return an error or something, and then have some function attached to it that will be executed when you reach the end of the stream. There's an interesting thing which I stole from Hacking with Andrew and Brett on, I think, HTTP 2 implementation, where they encounter a case where you would have to successively write to a writer, but you don't necessarily want to check whether your write succeeded at each write. So you don't want to check for the error. And they came up with a small helper interface, which is called StickyIrvWriter, which allows you to take a writer and successively write to it. And as soon as the writer fails, this arrow sticks around, and you can check for that error later. So you kind of save the immediate error checks on a couple of write calls, and then when you really want to make sure that everything went fine, you check for the error. So you have this shortcut where if an error occurred, it doesn't actually go further to the underlying reader, just returns. And then, of course, you have to check that at one point, but you can defer this a bit, which is also a quite interesting implementation. Yeah, we used IO_copy all along. It copies from source to dest. It uses an internal buffer, which is 32K bytes, I believe. And there's one copy optimization. If you have a source, a reader that has a write to method that takes a writer, or if the destination, which is a writer, has a read from method, which is a reader, then IO_copy will not use its internal buffer but defer the implementation of copying to these methods. So instead of going this loop, this arc through copy, if one of these methods are present, then the reader is passed directly into the writer's read from implementation, or the other way around, and which allows you to save some time. Okay, so to wrap this up, I hope I could show you a bit that these stream interfaces are very versatile. You all just need to implement a single method, and it allows you to adapt to a large number of existing components, which makes them, I think, very attractive. So if you encounter a use case, then you might want to consider it. Thank you very much. Like, we have like a minute for questions, or I'm also around, so yeah, happy to just come up. Yeah, please.
So my question is about IOUReader.
Yes.
I saw that the read method also mutates the state of included slides. Isn't this like a violation of the?
I think it should not retain. I mean, the write. In the case of the write, it's explicitly stated in the documentation, and in the case of the read, I think you should not retain the slice, but I think it's okay to use it, yeah, to mutate it in this case. But on the write, it would not be. Yeah. Mm-hmm.
Okay,